All right, let's pull back the curtain on the magic behind things like ChatGPT and all the AI assistants we use every day. We're going to get right into how they really work. So you ask an AI a question, right? And boom, out comes this perfect, well-written answer. It honestly feels like magic. But what is actually happening under the hood? What's going on inside that black box? That is exactly what we are going to break down. Now, before we get into the nuts and bolts of the technology, we have to talk about a huge fundamental shift in the whole philosophy of AI. Because this isn't just a new trick, it's a completely different way of thinking about how to build an intelligent machine.
And it really comes down to this fundamental trade-off. See, old school AI was all about hard-coded rules. If this happens, then do that. We called it a transparent box because you could trace every single decision. The problem? It was super brittle. The second it saw something new, it would just break. Modern AI completely flips that. We don't give it rules. We just throw unbelievable amounts of data at it and let it figure out the patterns on its own. This makes it incredibly flexible, but it also turns it into a black box, where figuring out why it made a decision is, well, it's a lot harder.
Okay, so how did we make the leap from just simple pattern matching to the incredibly powerful models we see today? Well, the answer lies in a single revolutionary blueprint that first showed up back in 2017.
So the early models, called RNNs, tried to read text just like you and I do, one word after another, in a sequence. But this was painfully slow, and worse, they had a terrible memory. They'd literally forget the beginning of a long sentence by the time they got to the end. The transformer architecture just changed the whole game. It figured out a way to process every word in a sentence at the exact same time. This solved the speed problem and the long-range memory problem in one single brilliant stroke.
But of course, a computer can't actually read words. It only understands numbers. So the very first thing any model has to do is chop up your text into smaller pieces, which we call tokens. Then, each of those little tokens gets turned into a very long string of numbers, a vector, that mathematically represents its meaning. And finally, because the transformer is looking at everything all at once, we have to add a little extra numerical code to tell it what the original word order was. Okay, now we get to the absolute heart of the transformer. This is the engine room. It's the one mechanism that gives these models their mind-blowing ability to grasp nuance and context. This is where the magic really happens.
Just look at this sentence. The animal didn't cross the street because it was too tired. Now, how do we know that it refers to the animal and not the street? I mean, a street can't be tired, right? For you and me, this is completely obvious. But for a machine, how on earth does it figure that out?
Well, the solution is this incredible mechanism called self-attention. Think of it like this. For every single word it's looking at, the model simultaneously scans the entire rest of the sentence and gives a score to every other word based on how relevant it is. So it quickly learns that for the word it, the word animal gets a really high score, while the word street gets a really low one.
The way it does this is pretty cool. It's kind of like a tiny little search engine running inside the model for every word. When it's processing the word it generates a query vector that's basically asking who or what is being described here. At the same time, every other word like animal and street has a key vector, which is like an index tag. The model sees a strong match between the query from it and the key from animal. That match tells it to pull information from the animal's value vector to get the context it needs.
Okay, so you've got this brilliant architecture, but it's still a blank slate, right? It's useless without any knowledge. That's where the training process comes in. And you can think of it like a really intense three-phase education that turns a raw network into an expert assistant.
Phase 1 is what we call pre-training. And honestly, the best way to picture it is locking the model in a massive digital library containing most of the internet and just telling it to read everything. Its only job is to get ridiculously good at one simple thing: predicting the next word in a sentence. But doing that simple task at an unimaginable scale forces it to learn grammar, facts, common sense, and even styles of reasoning. This is by far the most brutal and expensive part of its entire education.
So after it's basically read the whole internet, the model has all this general knowledge, but it doesn't really know how to do anything useful. It doesn't know how to be a helpful assistant. That's where phase 2, fine-tuning, comes in. We give it a much smaller, curated curriculum of high-quality examples, like thousands of question and answer pairs. This is where it learns how to actually follow instructions and perform the tasks we want it to.
And for the final phase, it's like the model gets a human mentor. This is a process called RLHF, or reinforcement learning from human feedback. Here's how it works. We have human reviewers rank different AI answers to the same question, from best to worst. We then use that data to train a totally separate reward model whose only job is to learn what humans like. The main AI is then trained to generate answers that get the highest possible score from this reward model. This is the critical final step that really aligns the AI to be, helpful, honest, and harmless.
So, we've designed the blueprint and we've put the model through school. But, and this is a huge but, this whole process also bakes in some fundamental flaws. It's so important to understand that what we've built here is an incredibly powerful tool, not a perfect thinking mind.
I'm sure you've heard the term AI hallucinations. That's when the model just confidently makes stuff up. The thing is, this isn't some weird bug, it's a totally natural result of how it was trained. Remember, its core underlying goal is just to predict the most statistically plausible next word. It's optimized to sound fluent and correct, not necessarily to be factually correct.
And then there's the problem of bias. Because these models learn from text written by us, by humans, they can't help but learn our biases too. The good, the bad, and the ugly. This quote really nails it. The bias we see in AI is just a mirror reflecting the biases already floating around in our society, embedded in the mountains of text we fed the machine in the first place.
And on top of all that, it's just really important to remember a few other key things. Its knowledge is totally frozen in time. It has no idea what happened yesterday. It has a limited short-term memory or context window, so it can get lost in really long conversations, and maybe most importantly, underneath it all, it doesn't truly understand anything. It's just a world-class, brilliant pattern matcher. And of course, the energy and computational cost to do all this is just astronomical.
So when you step back and look at the whole picture, you're left with this really fascinating question. Everything we've seen, from the architecture to the 3 phases of training, is all designed to build an incredibly powerful pattern-matching engine whose only real job is to predict the next word. So I'll leave you with this. Is that really intelligence? It's something to think about.